Good morning, everybody. How are you all doing today?
Hi.
Welcome back to Galois Theory. Sorry, I screwed that order up. Let's try again. Good morning, everybody. Welcome back to Galois Theory. How are you all doing today? That feels better.
Okay.
Cool. Hope you all enjoyed your Thursday off from class. Although I know all of you worked hard on homework 6.5. So it wasn't really a full day off. Saw many of you at convocation, either in the crowd or singing, but it's good times all around. Plan for today. Whoa, today's the big day where we're going to introduce the big result with an example.
Does it have the word Galois?
It may have the word Galois in it.
Look at the agenda and see the word Galois.
Indeed. Got my usual office hours this afternoon, 1 to 2, tomorrow 11 to noon, and 1 to 2. Post new homework. Homework 7, it's due Tuesday. It's going to be the exact same thing we're doing today, except for x cubed minus 2 instead of x to the fourth minus 2.
Oh.
Ooh.
Sounds like a deep freeze.
Yeah. Although I think I refer to it as S3 in the homework, but yeah.
That was an excellent Mickey Mouse earlier also.
Thank you. Any questions or comments before we get started for today? So, horse walks into a bar, goes up to the bartender, asks for a drink. Bartender pours the horse a drink. The horse guzzles it down. Bartender turns to the horse and says, hey, would you like another one? Horse says, I think not, and promptly vanishes. See, normally this is a joke about Descartes, but I wanted to make it about a horse because, you should put Descartes before the horse.
I know I've heard that one before.
Probably from me, yes.
Yes, from you.
Alright, and with that, let's get into today's example, x to the fourth minus 2. So, last few classes we've kind of built up all the necessary pieces to talk about what we're doing today. We talked about normal extensions, which are just field extensions, which also happen to be splitting fields for some polynomial over your base field. We talked about separable extensions, which are the ones where minimal polynomials don't have repeated roots. So anything over q, for instance, we showed has to be a separable extension, or degree characteristic 0 field extensions in general. And what we're going to do today is we're going to do a deep dive into x to the fourth minus 2. We're going to compute the Galois group. So in other words, we're going to find a splitting field of x to the fourth minus 2. We're going to find the Galois group of x to the fourth minus 2 by looking for automorphisms of that splitting field that fix q. Base field's going to be q for today. And then we're going to look at some interesting stuff that happens with the relationship between subgroups of the Galois group and intermediate field extensions, meaning fields that happen to live between q and whatever our splitting field turns out to be. So, start things off, I asked you all last time to find me a splitting field for x to the fourth minus 2. What did you all find?
Wasn't it?
You didn't do your homework, I'm not asking you. I'm just kidding. Yes, Emily Rose?
Wasn't it 4th root of 2 minus 4th root of 2, I 4th root of 2, and minus I 4th root of 2 that were the roots, so we needed I and 4th root of 2?
Yeah, so over the complex numbers, we know this factors into linear terms as x minus 4th root of 2, x plus 4th root of 2, x minus I 4th root of 2, and x plus I 4th root of 2. So what do we have to adjoin to q in order to get our splitting field? Our L, so to speak. And
I and 4th root of 2.
yeah, we need 4th root of 2. 4th root of 2 isn't enough on its own because q adjoin 4th root of 2 only contains real numbers. We need something containing I 4th root of 2. But if we also adjoin I, it turns out that's enough to give us all the roots that we need. So we got our splitting field. And now I'm going to look for automorphisms of q adjoin 4th root of 2 and I that fix q. So in other words, I'm going to look for the Galois group, so to speak, of L over K. So, you know any automorphism is of L is determined by where it sends 1, 4th root of 2, and where it sends I. Where if we know where some homomorphism maps these three elements to an L, then we can just take that since any elements in L can be written as products of these things, we can use the fact that we're working with homomorphisms to determine where anything else gets mapped to. So, Eleanor, what can 1 get mapped to? 1, very good. Eleanor, what can 4th root of 2 get mapped to?
4 root of 2.
It can get mapped to itself, certainly.
Or I.
Or I?
Maybe.
Don't think it can
No,
get mapped to I.
Negative 4 root of 2.
They can have that.
I 4th root of 2 and negative I 4th root of 2.
Turns out those are the only 4 options. Why is that?
I can't think of any.
Shut up. Like it?
Because 4th root of 2 is a root, so it can only map to, it can only map to a root of the, of x to the 4th minus 2.
Yeah, we know that if roots of irreducible polynomials have to map to in Q have to map to other roots of the same irreducible polynomials in Q. That was a theorem we proved a week or 2 ago at this point. So in other words, since 4th root of 2 is a root of x to the 4th minus 2, which turns out to be irreducible over Q, that tells us that the only elements in L that 4th root of 2 can possibly map to are the other roots of x to the 4th minus 2 in our splitting field. In other words, plus or minus 4th root of 2 and plus or minus I 4th root of 2.
Why do we have to include where an automorphism maps 1 to if?
Because I like to, because it always maps 1 to itself, because I like reminding myself of that.
Okay.
I mean, you're right, this is going to be the case in any extension of Q. But that's mostly because most of our examples that we've done have been in Q specifically. And it is always kind of important to know what elements have to map to what in order to determine what's going on in your base field. Just so happens that if your base field is Q, then knowing where 1 maps to is enough to know where anything else maps to. Because any A over B can be written as some quotient of 1 plus 1 plus 1 over 1 plus 1 plus dot 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 plus 1.
And because, I mean, we had one mapping to non-1 things in our homework with over C1 PC because it was 6.
Oh, that was different, yeah. When we were looking at automorphisms of C mod
But it does mean
PC.
that 1 doesn't always have to map to 1 if your base field isn't Q.
Correct. Yeah. I mainly do that as a reminder to myself, as a reminder to us. But you're right. The fact that 1 has to map to 1 means that whatever our automorphisms do doesn't really care about that
And besides,
top line there.
we've made progress. We write something down and we made progress.
Yeah, don't you like making progress, Eleanor? Aren't we progressive at this school? Don't answer that. How about I? What are the possibilities for where I can map to in automorphisms of L over K? Lincoln.
E to the I pi halves, e to the
Someone else.
I pi halves.
I and negative I.
I and negative I. Why those two specifically?
Because if I is the root of some polynomial, then we know that negative I also has to be a root in that polynomial.
If it's a polynomial over Q.
If it's a polynomial over Q.
So since I, for instance, is a root of the irreducible Q polynomial x squared plus 1, I necessarily has to map to a root in L of the same polynomial.
Yeah.
Which in L, that has roots of plus or minus I. So there we go. That's our options for where, and kind of extending this out via homomorphism is enough to tell us where any automorphism of L that fixes K is going to map things to. So what does this give us? I claim D4 is isomorphic to this automorphism. In other words, D4 is isomorphic to the Galois group of our polynomial. And to do that, we've already kind of looked at an example of this. We just kind of saw what maps to R, what maps to S. This time, I think it's going to be useful to go the other way around. And instead of starting with automorphisms and mapping automorphisms to elements of D4, instead, we're going to map elements of D4 to particular automorphisms. That'll make things a little easier for us later on. So D4 has 8 elements. Identity, R, R squared, R cubed, S, RS, R squared S, and R cubed S. So we need to set, if we want to define a isomorphism here, a group isomorphism from D4 to the automorphism group, we need to somehow, we need to show where phi maps each one of these. So start off simple. What's the phi of the identity element going to be? Well, if you have an isomorphism, identity element has to map to identity element. So what's the identity element of this automorphism group?
1 maps to 1.
1 maps to 1. Well, okay, that literally every element's automorphism group has that. Can you narrow it down for me?
Aren't elements in the Galois group just mappings? Oh, you're going to say all of them. Okay. Well,
Yeah, I want to say what everything else maps to.
And fourth root of 2 maps to 2, and I maps to I.
Yeah, in other words, just the identity function, where everything maps to itself. Wow.
I'm actually noticing that there's now 4 wheelie chairs instead of 3 instead of 2.
Gotcha.
Oh, yeah, no, we're amassing an army.
I know. I noticed this morning when I came in.
I didn't even do that. I would, though.
Oh, okay, because I totally suspected you.
It wasn't big yet.
How about R? R needs to map to, what's important here is that R needs to map to some automorphism of order 4, meaning something that if you compose 4 copies of it with together, you get back the identity function. So Matthew, what would be a way that we could pick where each of these maps to that would give us something of order 4?
I feel like there might be multiple options for this.
I feel like I would agree with this.
So I think you go 1 to 1, and then I think you go,
No options there.
yeah, and then you go 4 root 2 to I root 4 of 2.
I times 4 through 2.
You have that, and then I think you can go either I to. I haven't thought this out actually. I know for sure you can go I to I, but I think you might also be able to go to negative I also.
You could. I like this one. I think that's the simplest one. Mainly because R is a simple thing, and while we could have R, and while if we had I mapped to negative I, that is also an automorphism of order 4. It's a messier one than this, and since R is a nice simple thing, I want it to map to as nice and simple a thing as possible.
Could you also do the same thing with negative I, 4 root 2?
You could.
Okay.
Yeah. What you can't do is have 4th root 2 mapped to either of these two.
Right.
Because that would either give an automorphism of order 2 or order 1, depending on what I maps to as well.
And then what is S in this case? Because I'm from Hutchinson, so I don't know what kind of flip that is.
Oh, you're from Hutchinson, so you don't know anything. Okay. Excuse me. So think of it this way. 1, 2, 3, 4 are the vertices of a square.
Yeah.
R corresponds to a single 90-degree rotation of the square. It can either be clockwise or counterclockwise, doesn't matter which, as long as you're consistent.
Right.
S means you have to do some reflection. I think the way I defined it in 410 was, did I use that diagonal? Did I use the other diagonal?
I thought you flipped it horizontally.
I did that. It really doesn't matter as long as you're consistent about it. You reflect over that, so basically 1 and 2 swap places, 3 and 4 swap places.
Okay.
But S corresponds to a reflection, something of order 2. R corresponds to a rotation of order 4 is what needs to happen. And whatever exact rotation and reflection you choose isn't super important for determining, because whatever it ends up being, you get isomorphic group structures. as long as you're consistent about it. Yeah, Matthew, I like the choice of for where R gets mapped to. So with that, what about R squared? Lincoln?
Well, you need it to be, phi of the, phi of R composed with itself, or.
Correct.
So,
Here we don't have any choice. Once we decide what phi of R is, that necessarily tells us that phi of R squared, since we're dealing with something that has to be a homomorphism, is phi of R times R, which is technically composed with, which needs to be phi of R composed with phi of R.
So, 1 goes to 1, 4th root of 2 goes to negative 4th root of 2, and I goes to I.
Yeah. If we do R twice, I maps to I, maps to I, so I still is stationary. 4th root of 2 maps first to I 4th root of 2. And then if we see where does I 4th root of 2 map to? Well, I is mapping to I, again, 4th root of 2 is mapping to another copy of I 4th root of 2. So you end up with I squared 4th root of 2, or negative 4th root of 2. And finally, about R cubed. Should have done this on a side note, so we're going to defer back to this. Yeah. Andrew?
1 goes to 1, 4th root of 2 goes to minus I, 4th root of 2. Goes to
Yep. Similar procedure, you just compose phi of R squared with phi of R, and you end up with 4th root of 2 goes to negative I 4th root of 2. I still maps to I. So no matter how many times you take phi of R composed with itself, I is always going to get mapped to I. So how about S? Now we need to introduce a reflection, something that's going to be of order 2. No, you're on timeout for the time being. Eleanor, where could S map to?
1 maps to 1, 4th root of 2 maps to 4th root of 2, and I maps to negative I.
Yeah, we've exhausted all the possibilities at this point where I maps to itself. So for the rest of these, we're going to need I has to map to negative I.
Left across the real axis.
Sure, why not? That's the way you want to think about it. How about phi of Rs? If we were to take phi of R and then compose it with phi of S.
Oh, well, don't spoil it.
Sorry.
I keep writing 1 goes to I.
Oh, okay.
There. It's a mystery. Parker, where do you think 1 maps to?
1, maybe.
Incorrect.
No.
It maps to e to the 2 5. I don't know what it maps to.
See, I thought Lincoln
No.
was on timeout for a reason.
He is. Now I have to put myself in timeout. Isaac, take over.
So,
Actually, no. Eleanor, take over. That's more. That would be more funny.
this is
All right, Eleanor. Where's 4th root of 2 gonna map to?
That should map to I 4th root of 2.
Why's my 1 so big? And I?
Negative I.
Well, let's see. If we take
have to go to negative I to the 4th root of 2.
was what?
Does it have to go to the negative I to the 4th root of 2?
Well, we know phi of Rs has to be phi of R composed with phi of S.
So then yes.
So since these are now determined at this point, Rs is also determined at this point. Because let's see what each of these maps things to. Well, 1 maps to 1. Oh, hi, Seamus. Maps to 1. I'm assuming that's Seamus. Yep.
No, it's someone who's not been in this class before.
I, let's see, phi of S, because remember, we have to read these from right to left. Nah. Phi of S maps I to negative I. And then phi of R maps, well, since I maps to I, negative I has to map to negative I. And then phi of s maps fourth root of 2 to itself. And then phi of r maps fourth root of 2 to I fourth root of 2. So if you're specifically looking for a homomorphism, Isaac, yes, then it's determined. If you're not looking for a homomorphism, well then pretty much anything can map to anything.
Or you could do it the hard way and decide RS first and then work.
Yeah, but no.
Why would you ever do that? That's great.
There's a reason why I wanted Matthew to have the simplest one go to R. Well, the simplest one that's not this, go to R. Simplest order 4 one go. Anyways, how about R squared s? Here we need to compose phi of R squared with phi of s. So at this point, I think the rest of them are determined by what we already have.
Gonna make a wild guess and say that 1 goes to 1, fourth root of 2 goes to negative fourth root of 2, and I goes to negative I.
Well, let's see. S maps I to negative I. R squared maps negative I to negative I. So I has to map to negative I. Fourth root of 2. Let's see. S maps that to fourth root of 2. R squared maps that to negative fourth root of 2. So it's going to be negative fourth root of 2. And I'll leave it as an exercise to you all to prove that 1 has to go to 1. So I would agree. And then at this point, well, at this point we could use the fact that we want a bijection to say this has to map to literally the only possibility that's left. Or you could compose R cubed with f, phi of R cubed with phi of s. And we'll
Because if those two things come out to something different, you have a problem.
well, then that means that my claim has probably been debunked. or well, either that or if we have some error been somewhere in here.
Like we did last time when we tried to do S. What?
That didn't happen.
All right, there we go. Turns out this gives us an isomorphism. No, I'm not proving this is an isomorphism. I hope everybody believes that this is 1-to-1 and onto.
Haven't we been acting under the assumption that it's a
Yeah. What I'm just saying is technically proving that it's a homomorphism involves more steps.
But we've been assuming it's a homomorphism.
We kind of have. It turns out to be one. I just don't feel like going through the work to check that.
We're not assuming it's a homomorphism, and more building it so that it must be a homomorphism.
Pretty much. If you want to check, you could do like phi of A plus B.
Goes with B?
No, A of take an arbitrary combination of these things, and then add it to another linear combination to show that phi of that first thing is
Add it to or compose it with?
compose it with. Yeah.
And
You know what Anywho, any questions or comments about how we constructed our group isomorphism between D4 and our Galois group of x to the 4th minus 2?
Well, with this particular polynomial, it's really nice because you can draw the roots on the complex plane and then connect them, and you will just have a square just sitting on a corner,
Bingo.
and then
There's some nice geometric interpretations, which you don't know the half of yet, by the way.
yeah, sure.
And in that scenario, 1 mapping to 1 is like the origin staying in the same spot.
Yeah, because if you're doing like a rotation or reflection of the complex plane, assuming it's centered at the origin stays the same. So
if you extend this to infinite.
And moving on.
Transformation.
So, next question.
do we get
I want a subgroup lattice.
a
Oh wait, oh yeah, I forgot to give you your packet. Oh, silly me. Oh, why are you just now reminding me?
Because I wasn't sure when, I had just pulled out my old packet and taking notes on the back.
It's true, we already did look at this example before, although not into as much detail and fully exploring the homomorphism, which we're going to want to do which we'll need here in a few minutes. So I'm on page 2 now. All this is supposed to be page 1 in the packet.
Let's start by finding it.
Let's find a subgroup lattice for D4. So first things first, D4. I need subgroups. And I need 10 of them.
There's
few of them.
The identity.
The set container.
Fit.
Spend art too many times.
If you hadn't said it, Lincoln, I was going to. Matthew.
All the R's and E.
So I'm just gonna say group generated by R. It's gonna be nice to have a generator for each of these subgroups, or generators in case it's not a cyclic subgroup. Pardon?
Group generated by, yes.
Yep, S and, so in other words, S and the identity. Group generated by R is R squared, R cubed, and the identity, because R to the fourth is E in this group. Lincoln?
Group generated by R cubed S.
Group generated by R cubed S. Yes, which just consists of R cubed S and itself.
It does not consist of the identity?
And the identity, sorry, that's what I meant. It consists of itself and itself. No, it consists of the identity element and itself. That's what I meant to say. Matthew?
R squared S. That's just that one, right? Because it.
Group generated by R squared S. Just making sure when I look at my notes that I didn't reference it with a different generator. What else? Hey, there's still at least one cyclic one left.
R squared.
Yep, just R squared in the identity. I think there's a lot of subgroups of order 2, by the way. Lincoln?
RS. The group generated by RS.
Andrew?
Yeah, also the whole
Hey, look, a non-cyclic one.
I was going to say, the group generated by R and S
All right. The group generated by R and S
is the whole thing.
equals the whole thing, yes. So we still have 2 more.
This is not cyclic, but the group.
Either of the remaining ones are cyclic.
Yes, the group consisting of E, R squared S, and R squared S.
The group consisting of E, R squared, R squared, comma, S, comma, R squared S. Gotcha. Yeah, so that's going to be this one. Group generated by R squared and S together. And one more. Eleanor?
The group generated by R cubed and S.
Group generated by R cubed and S.
That should be the.
That might be the whole thing.
That is the whole thing, yes.
Really?
I just have to think about that for a second. Yeah, because
Yeah.
R cubed generates the same elements R does.
Yeah.
Yep, forgot about that.
Abby?
E R squared R cubed S and S.
E, R cubed S,
That should be
what did you say?
Um,
E, R cubed S.
I said R squared and then I think I want to say S. I'm trying to do the. It's the same thing with the E's.
I mean, it's
R180. Yeah.
So this ends up giving you the identity R squared, RS, and R cubed S.
Dude, that is this still equivalent to R cubed S too? If you were to do it.
Yeah, you could. Yeah, I think.
Okay.
Yeah, if you did put that in there, it would give you the same thing.
Okay.
As much as possible, I'd like to eliminate exponents whenever we can.
Okay.
Very simple. Cool. Let's make a subgroup, lads. Oh, Dr. Ursula, what does that mean? I want a picture in which we have all of these drawn out, where it's clear from the picture which of these are included in which other ones.
What does that mean? Oh. E's in all of them.
Say what?
E's in all of them.
Yeah, E's in all of them. Which normally, if you're, I don't know what you've all seen of subgroup lattices, normally that means you put E at the bottom. Say it's like contained in all of these. But we're going to get a little bit funky. And we're going to put E at the top.
That's right.
That's kind of cool.
We're going to take the usual subgroup lattice and flip it upside down.
That's kind of funky.
Yeah, it's kind of fun. Turns out, any of our subgroups that have exactly 2 elements, there can't be anything intermediate. So we're going to get subgroup generated by S, subgroup generated by R squared S, subgroup generated by R squared, subgroup generated by RS, and subgroup generated by R cubed S.
What do you know? You can't add half an element.
what do you know? You can't add half an element. This thing has one element. These all have two elements. And so there can't be anything intermediate between here and here because you can't have something between one element and two elements. 1.5 elements just ain't no good. So here's one. What's a subgroup of D4 other than D4 itself that contains everything in the group generated by R squared? Andrew?
Subgroup generated by R.
Yeah, subgroup generated by R. This has all the rotations, R squared, R cubed, and the identity. This just has R squared and the identity, so this is properly contained in that.
But the question is there a 3-element one? Because we went from 2 to 4.
Well, if I recall correctly, we had this nice Lagrange's theorem that says the order of subgroup has to divide the order of the group. Is 3 a divisor of 8?
Not in the
Right.
Nope. So all of our subgroups have to have order either 1, 2, 4, or 8. Any, actually it does in the irrationals, not the integers, I believe you mean.
That's what I meant.
Don't we always divide, even if we're in the rationals, don't we divide for the integers anyways?
Yes.
Well, not in this class.
Oh, not
Because
in this
everything's a unit.
All right.
Different units.
What's something else that contains all of these? That contains S, R squared, and the identity element.
Generated by R squared S.
And S.
And S, yeah.
Not R squared
I'm
S.
sorry, R squared.
Who's on first here?
What's on second?
I don't know who's on third. Oh goodness. Finally, what contains all of these?
My guess is it's the only one left.
My guess is you're correct.
That's a scary guess to make.
Say what?
I guess we did already put the proper one in there, somewhat presumptively.
We put what in where, somewhat presumptively?
But we stuck it at the bottom.
Yeah. Well, these are all subgroups of order 4. You can't have a subgroup of this with that property. You can't have anything intermediate between subgroup of order 4 and subgroup of order 8 because then you'd have to have order 5, 6, or 7, which means it can't be a subgroup of a subgroup of order of a group of order 8.
It looks like that.
That's the right pretty diagram right there, I think what
All right. And here, when we say A and then B, what's the relationship between A and B in this picture?
A is the subgroup.
So here, subgroups are above normal groups, which is kind of the opposite of how you usually see a lattice diagram of this sort being drawn.
Why are we doing that though?
I don't know, for fun, because I'll enjoy tricking you.
No!
It's easier to generate from the bottom up.
Well, I don't know. Actually, fine, I'll admit, I do know there is a reason, but we will see it later. Any questions or comments?
Well, let's have a look at this.
Look pretty.
It's very symmetric.
It is very symmetric.
Is that because it's an even
Symmetric group.
Oh, this is not a symmetric group, madam.
If you did a symmetric group, it
But
was
subset
is
or
it D4
It's a subgroup of the symmetric group.
So it's fine.
Are all of them really pretty or just
We
like?
can have infinite symmetric groups. Like S infinity.
Wait, what was the symmetric group again?
S sub n, permutation of like 1 through, of the set of numbers 1 through n.
I thought S4 was isomorphic to D4.
Nope. S3 is isomorphic to D3.
Well,
Remember, S sub n has order n factorial.
Right.
4 factorial is not 2 times 4. But 3 factorial is 2 times 3.
Every finite.
Alright, completely new and I'm sure completely unrelated question to what we just did.
Is this on the next page?
Yes.
It's also problem 3.6.1.
Which someone should know, and by someone I mean everybody in here.
I'm sorry!
I want to look for intermediate subfields. I want to find subfields E, or with K, is contained in E is contained in L. All right, last thing I ask you all to find. Emily Rose, give me one.
K is contained in E. Let's go with Q adjoint 4th root of 2.
Q adjoin 4th root of 2. Last one. Pete?
Q joined I.
Q adjoined I. Lincoln? You're out of time now.
Q adjoined I 4th root of 2.
Q adjoined I times 4th root of 2 or I comma 4th root of 2?
Times. It's an intermediate stuff.
There you go. Eleanor? Yeah, I have the equal signs here, so Q counts.
Q adjoint square root of 2.
Q adjoins square root of 2.
Whoa.
Because square root of 2 is 4th root of 2 squared, so anything that's in Q adjoint 4th root of 2 is automatically going to be in Q adjoint root 2.
You would join square root of 2 and I.
Ooh, Q adjoined square root of 2 and I. Yep. Matthew?
I mean, could you say something like Q adjoin I square root of 2? Or is that?
Q adjoined I times square root of 2?
Yeah.
You could indeed. Because I and square root of 2 are both, because if I and square root of 2 are elements in L, then I times square root of 2 should certainly be an element in L. All right, we've got 7. Anybody have any more? Emily Rose?
L.
Oh, okay. Yeah, take the obvious ones. Yeah, we got the whole thing. Any others?
Let's see. What do I think we're missing based on what we have over here?
I don't know. How many more do you think there are?
I think there may be 2 more.
Wow.
And I think one of them might map to R cubed S, and one of them might map to R squared RS.
Well, I don't know what you mean
No.
by map to.
We might have already.
No, I think we might have gotten that one, you're right.
I don't know what you mean by map to in this case.
I don't know either. I don't know what
Okay,
we're doing
okay.
because I didn't do the homework.
We
But
need a
Isaac?
we need a Q adjoin square root of 2 and I 4th root of 2.
Like that?
Yep.
do we know?
That's just Q adjoin I 4th root of 2 because if you take this and square it, you get negative square root of 2. And since you have to have the negative, if you take the negative of this thing squared, you get that. So, I mean, you're technically right, but that's already accounted for.
Okay, then I square root of 2 and 4th root of 2.
I square root of 2 and 4th root of 2?
Yeah.
Nope. Because that's equal to 1 of these.
I think it's the whole thing, right?
No.
It should be the whole thing.
Yeah.
Yeah, because this gives, if you square that, that gives you square root of 2, and if you take that over that, that gives you
Oh.
I, and since that contains I and 4th root of 2, that would give you the whole thing. Yeah.
Oh, really?
Oh, wait, that's.
Huh. Turns out there are 2 more. They are much harder to find than the others. Well, it's easy to find more, but it's harder to find more that are not secretly equal to one of these. I'm going to say Q adjoins some alpha, Q adjoins some beta.
Hold up. We're not going to find them?
Oh, we will. Just not yet.
But we
Those
gave
are
them,
really special.
we gave them the funny letters, which
We-
means it's gonna be like a theorem or something.
No.
Oh.
Well, sort of. But
Oh,
we'll compute. We're going to have a purely computational way of finding it. Let's form a subfield lattice.
Oh, so
Except-
something that makes
Except this time, I'm going to put the biggest one up top.
science.
And the smallest one going at the bottom. All right, second level up from the bottom. And in this case, when we say and we have an A on top of B, what that's going to mean is that B is a subfield of A. So I'll go ahead and do the next level up, just because I'm a nice guy. Q adjoined root 2, Q adjoined I, Q adjoined I root 2. Question, how do I know nothing lies in between here and here, here and here, or here and here? What's specific about those three extensions, unlike the other ones in the list, that means nothing can lie in here? Andrew, did you? Specifically, what can we say about the degree of these extensions? They're all 2. So can you have something, an intermediate thing, in order 2 degree 2 extension? No, because if you had some like A in here, or Q's subfield of that is a subfield of that, you'd have to have the degree of this extension times the degree of that extension comes out to 2.
And you can't have half a degree.
Which means one of them is 1 and one of them is 2, and if one of those extensions is degree 1, then it has to equal the whole thing. You all had this on a homework where we said if you have an extension that's of prime degree, a field extension of prime degree can't have any intermediate subfields. So since these are all degree 2 extensions, there can't be any subfields between that and Q.
We have a moderate problem. We don't know what alpha and beta are.
Oh, that's a
We have to
problem.
find a way to figure out the degree of the thing.
Oh, that's a problem. So what is Q? So what is something that's intermediate between Q adjoined root 2 and Q adjoined 4th root of 2 and I?
Q adjoined root 2 and I.
Q adjoined root 2 and I. Put that one here. Turns out and N. And for that matter, N. Turns out that contains all of these. They're all degree 2 extensions, so we know there's nothing in the middle. Eleanor, what else is something that contains Q adjoined root 2?
Q adjoined 4th root 2.
Q adjoined 4th root 2. Get that one out here. Turns out that doesn't contain Q adjoined I or Q adjoined I root 2. In particular, Q adjoined 4th root of 2 is still a subfield of the reals, and these contain imaginary numbers. Lincoln?
For that matter, Q adjoined I times 4th root of 2.
Q adjoined I times 4th root of 2. Also be another one that goes here.
So what's the stuff in between?
There isn't nothing in between. By the way,
No, I mean like.
what's the degree of this extension, Q adjoined 4th root of 2 comma I over Q adjoined 4th root of 2?
Q2.
Which means there can't be anything in between. And the same is true for these as well. So where does this very suggestive diagram, where would you guess Q adjoined alpha and Q adjoined beta live?
Somewhere over there.
There.
Yeah.
It's going to turn out to be the case that you'll get a Q adjoined alpha here and a Q adjoined beta here.
Gee, it looks like the other diagram.
Wow, it sure does.
Except there are some strange because they're upside down of each other.
What the heck?
Holy moly.
That's kind of crazy.
So let me ask you this. I drew this diagram in a very specific way.
Clearly.
What's the relationship, for instance, between S and Q adjoined 4th root of 2? Because that's a field extension, and this element of D4 share special relationship. If we look at where phi of S is mapping here. What's specific about Q adjoined 4th root of 2 and how it could relate to subgroup generated by S?
The subgroup generated by S is isomorphic to the Galois group of Q adjoined 4th root of 2 over Q.
Okay, but without introducing other Galois groups, just using this one,
They have the
what
same
does S
order.
do? What is S doing to elements that are in Q adjoin fourth root of 2?
It's keeping them all the same.
It's keeping them all the same. Anything that's in Q adjoin fourth root of 2, like 1 for instance, is being kept the same. Fourth root of 2 is being kept the same.
Oh my son.
Here's what the relationship is between our diagrams. That's why I wish I'd done this on a sideboard. I'll do this over here.
But then Lydia couldn't see it.
Lydia,
Makes it hard.
Okay.
I mean, Lydia gets to see my notes as I post them on Canvas. So she can, oh, fine. All right, Parker, fix it.
It's gonna.
We're gonna say that Q adjoin fourth root of 2
I need to please wait while the
is the
system
fixed
starts up.
field
Uh-oh.
Oh no.
Oh, no, can't do that.
of S under the map phi.
I'm just waiting.
Oh, now you turn the projector
I'm
on.
just waiting for the system to start up. This is the college's fault.
Lydia, we care about you. You're making my life difficult.
Technology.
So what do you think this means? Q adjoin fourth root of 2 is the fixed field of S under the map phi. Well, it means if you take phi of S of A, where A is some element in Q adjoin fourth root of 2, what do we get back? You just get back A.
There we go.
Keeping in mind, phi of S is actually itself an automorphism.
We're still over there. Okay, I didn't know
This
that.
thing right here is an element of the automorphism group of L over K, phi of S. It's the automorphism that maps 1-to-1, fourth root of 2 to itself,
Oh geez.
and it swaps I and negative I.
You're making this real difficult to understand.
Turns out Q adjoin fourth root of 2 is the fixed field of S under the map phi.
And you want it to be normal. Wait, how long are you gonna be over on that for?
As long as it takes to make you feel the pain that I feel,
I'm already feeling it.
well then I'm gonna keep going.
Oh,
So for instance, what would you guess is the fixed field of R under phi? In other words, if we look at what R is doing, what elements are going to get mapped to themselves?
Q and I.
Q adjoined I. Q gets mapped to itself. I gets mapped to itself. Anything involving fourth root of 2, phi of R does not map to itself. So we can say Q adjoined I, it turns out, is the fixed field of R under the map phi. Which, wouldn't you know it, N appears in the same place as N. You just need to leave the camera alone. Lydia, I apologize for this.
Corporate needs you to find the difference between these two pictures.
there we go.
Now, what relationship does things in that lattice have to things in this lattice, if you had to guess? These are the fixed fields of the corresponding elements in the lattice here. And that is the fundamental theorem of Galois.
Oh my son.
If you happen to have a Galois extension, meaning an extension that is normal and separable, which this one is, this is a normal separable extension. It's normal because this is a splitting field of something. It's separable because it's over Q, and every extension over Q is separable. Then, if you were to look at all the intermediate subfields between K and L, and all the subgroups of your automorphism group, you get a nice one-to-one correspondence between the two. So for instance, the fact that there are 10 subgroups of D4 tells us there should be 10 intermediate subfields over here.
So how are we gonna find out?
We need to see what fixes.
I guess we'll have to use what's the fix.
Yeah.
I guess we'll have to find what's the fixed field of RS and R cubed S.
Whoa.
Which is very not obvious.
It's not obvious, no. It turns out you have to do some algebra to get there.
Is it also?
But that's how we would go about it. I mean, we'll do that here in just a minute once I answer some questions.
I was gonna also ask, does that mean that if you multiply, I don't know what you call like conjugate groups, I guess, if you wanna call them that.
Conjugate of groups.
I don't
Such
know, I don't know,
madness.
like, what are we gonna call the relationship between, like,
This thing and this thing?
that and that, yeah. Well,
I don't know. I wonder if we have
No,
some
but
nice phrase that we can use to refer to the relationship between these
Okay,
things.
well, if you take the degree,
Hey, that sounds like a good idea. I might have to steal that, James.
if you take the Galois correspondent of,
Correspondence.
okay, dude, okay, dang, I can't do that.
So, sorry, go ahead.
If you take the multiples of the degrees, you, oh my god.
Alright, so
If you take the products of the degrees for any of the two corresponding groups or subgroups, you get 8 as a product for all of them. don't you?
correct.
Yeah.
In any path from here to here and any path from here to here has to multiply out to 8.
Right.
Turns out all of these are 2 in both cases.
Right, but
That's
if
not
you-
always going to happen, by the way. You can, depending on your example, you might have it where these are not all the same. For instance, if, I don't know, the path from the bottom one to the top one happens to be degree 6, for instance, they're not all going to be the same.
Oh.
I don't know where that might
I don't
occur.
mean that though. I mean like if you take like if you have the degree of Q 4th root of 2 adjoined, and the degree of subgroup generated by S, if you multiply them together, you get A. And if you take, the other ones.
Sure. So
the same
basically,
way, you'll
if you
always
take the
get
order
A.
of this over the order of this, you'll get 2. This over the order of this, you'll get 2. This over the order of this over the order of this, well, actually, flip what I just said around. The order of this over the order of that, you get 2. Order of this over the order of that, you get 2. Order of this over the order of that, you get 2.
Oh,
And the degrees of these extensions are going to nicely match up with the degree of the corresponding
but what you're
extensions.
saying is that's not always true.
No, that's always true. Assuming you have a Galois extension.
Okay,
You need to have a normal separable extension for any of this to work out. Otherwise, it's no good.
okay.
Like if you were just trying to look at automorphisms of Q adjoined cube root of 2 that fix Q, that's not a normal extension, so the lattices wouldn't necessarily turn out the same way. Y'all want to see something else that's fun?
Yes.
What are the normal subgroups here? Consequently, what are the normal extensions here?
Oh.
Give you a hint. This one, this one, this one, this one, this one, this one are normal subgroups. Which actually isn't too hard to show. Anything of index 2 is norm of the whole group. Meaning any subgroup that makes up half of your overall group has to be normal. So that's what tells you these are normal. Trivial subgroup and the whole group are always normal subgroups of the whole group. And this one, you just kind of check. Did I do this upside down? I'm just realizing something. Hold on, now I'm questioning myself. That's ordered 4, that's ordered 4, that's the whole thing, that's ordered 2. No, okay, I did it right. Okay, phew. I thought I made a terrible mistake for a second. This one is not too hard to check. This one is obvious. What are the normal extensions? Well, choose a normal extension of itself. It's the splitting field of, I don't know, pick your favorite rational linear polynomial. Yes, Eleanor?
What does the normal subgroup mean again?
Oh my gosh, what does normal subgroup mean? Oh my gosh, I don't remember my 410. It means the left and right cosets are all equal.
Oh, okay.
It's the things, in other words, you can quotient out by and get a well-defined quotient group structure.
What does a fixed field mean?
That basically means if you take any element in Q and join fourth root of 2, V of S maps that element to itself.
Okay.
It fixes it in place, in other words. V of S is an automorphism that if you took any element in Q and joined fourth root of 2 and plugged that into this automorphism right here, it would give back the exact same element.
Okay.
So like fourth root of 2 maps to itself, 1 maps to itself. These are things in Q adjoint fourth root of 2. I is not in Q adjoint fourth root of 2, and so I does not map to itself. That makes sense?
Yeah.
So this is a normal subgroup, or a normal extension, because Q is the splitting field of anything that already splits over Q. This is a normal extension. It's a splitting field of what polynomial?
X squared minus 2.
X squared minus 2. This is a normal extension. What's it the splitting field of, Isabel?
X squared plus 1.
X squared plus 1. This is a normal extension. What's it the splitting field of?
X squared plus 2.
X squared plus 2. This is a normal extension. This is not. What is this a splitting field of? This one's a little bit tougher. Technically, this is a splitting field of x squared minus 2 times x squared plus 1. Because in order for that to split, you need I for the second term to split, you need square root of 2 for the first term to split. This is a normal extension.
We started with it's
Yeah, it's a splitting field of the polynomial we started with, x to the fourth minus 2. A normal subgroup of D4, a subgroup of D4 is normal if and only if its corresponding fixed field is a normal extension. And that is why we call normal extensions normal, is because they correspond to normal subgroups in the Galois correspondence. Any questions or comments? So there's one last thing I want to do in this example, and that's what do we still need to find?
Alpha and beta.
Yeah, we still need to find what's that and what's that. So turns out it's not too bad to actually do that. By the way, all the stuff I said about what does the Galois correspondence preserve, the next packet is going to have the theorem stated out in full detail, so you don't need to necessarily have all that down in order to follow along. So, what is alpha? Well, we know alpha needs to be fixed by, I shouldn't have erased that diagram so quickly, what, RS? So we need phi of RS needs to have fixed field. Q adjoined alpha. So how do we actually find some element that phi of RS fixes?
I mean, you basically have to construct an arbitrary element of,
L.
yeah, using a basis of powers of 4 through to 2 and I, and then,
Yep.
and then,
Yeah.
do phi of RS on that
And set it equal to the original thing. Oh my gosh, do we need all of them?
Well, do you need all the fourth root of 2 exponents?
Yes, you big baby. I mean, you can get by with you if you really know what you're doing, but let's just do it with all of them. There's only 8, it's not that bad.
Okay.
Alright, let's take an arbitrary element alpha in the splitting field. So alpha is going to have form some constant times 1 plus constant times 4th root of 2 plus constant times root 2 plus constant times 4th root of 2 cubed plus constant, no that's not e, the 2.71 thing, times I plus constant times I 4th root of 2 plus constant times I square root of 2 plus constant times I 4th root of 2 cubed. And now we need to see where does phi of RS map all of this. Alpha equals phi of RS of alpha. It's not that bad. Keep in mind phi of RS is a homomorphism, which means we could just see what it does to 1, 4th root of 2, square root of 2, etc. And that's where each of these is going to correspond to. So where does phi of RS map to 1?
To 1.
It maps to 1. So where does A map?
Hey.
Yay. Where does 4th root of 2 map?
I 4th.
I'll underline these because this is what we need.
Whoa.
I 4th root of 2. So where does B 4th root of 2 map?
BI 4th root of 2.
All right. Where does square root of 2 map
So
to?
that means that BI 4th root of 2 is not part of this, right? Because,
So what's not part of what now?
well, alpha, we need B to be 0 because 4th root of 2 didn't map to 4th root of 2, right?
Well, keep in mind you could have, I don't know, maybe
That
some
could
relationship
have
between F and B.
Would it?
And B equals F is going to be a necessary condition to get out of this. Sorry, Lincoln, what were you saying?
Negative square root of 2.
So this is going to come out to minus C square root of 2. Keeping in mind, each of these coefficients, A through 8, are all elements in Q that come along for the ride. And so each of those coefficients, phi is going to map to itself. Phi of RS has to map to itself.
How did we get negative C?
That's Lincoln. Lincoln.
Is it just
Root 2 is
Squared.
4th root of 2 squared,
Yeah.
so it's I 4th root of 2 squared.
yeah?
How about 4th root of 2 cubed? Where does that get mapped to?
Negative I.
4th root of 2.
As 4th root of 2 maps to I 4th root of 2, so if you do that 3 times, you're going to get I cubed 4th root of 2, which is negative I 4th root of 2. How about EI?
Is it still cute?
Minus CI.
Minus O. Yes, maps to minus EI, because I maps to negative I, so EI maps to E times negative I. So, sorry, what were you asking, Seamus? I was too busy making lame jokes.
Oh, I was making another lame joke. I just said EIEIO.
Okay, good. I'm glad we have the same thought process. How about I 4th root of 2?
Would it negative 4th root?
What's that?
Would it be negative 4th root of 2 because you're multiplying?
We know I maps to negative I, 4th root of 2 maps to I 4th root of 2.
4th root of 2.
We get negative I squared 4th root of 2, which is just
Negative
4th root of 2.
That's what I said.
Oh, hey, maybe more seeming that we need that F and B are equal to each other.
Wait, did we say negative 4th root
Positive.
of 2?
No, 'cause
Negative
it's
I
squared.
It's negative I squared 4th root of 2,
Positive.
which is negative 1 times negative 1, which is 1 times 4th root of 2.
Wait, what?
Because I 4th root of 2, the I part of it maps to negative I.
Oh,
4th root of
so
2 maps to I 4th root of 2. So if we combine these, we get negative I times I 4th root of 2
Oh.
using the homomorphism property, which gives us that.
This is
Yeah, this is ribs. All right, how about I root 2? Lincoln.
I root 2.
Plus I root 2. Let's see, I maps to negative I, 4th root of 2 is going to map to negative 4th root of 2.
Yep.
And so the whole thing will map to negative 4th.
What?
Negative I root 4th root of 2. Negative I square root of 2, excuse
Yes.
me.
Yep.
Which is I plus I square root of 2.
Well, that just stays the same. What do you know?
Oh, hey, maybe G could be anything. And finally, how thoughts?
I'm just gonna say likely I expect it's gonna go to the 4th root of 2 cubed, and then
Oh, it's
h has to
totally
equal
plus
d.
H.
But I don't actually have the reason that that works.
Wait,
Well, you can just see where does 4th root of 2 cubed map to? Well, that maps to negative I 4th root of 2. I maps to negative I, so the whole thing is going to map to negative I times negative I 4th root of 2 cubed. And negative I times negative I is negative 1, so this comes out to negative 4th root of 2 cubed times h.
This is real gobbledygook over here.
Some real gobbledygook over here, huh? It makes you feel better. If it makes you feel better, you don't actually end up having to do any of this in the homework.
I didn't think so, because we have a smaller slate field, don't we?
Yeah, basically, I expect, basically all this intermediate subfields, you can find like how we found the non-alpha beta ones over
Okay,
there.
we're doing it for a cubic instead.
Okay, so if these are equal to each other, what does that give us?
Well, G is really cool.
Well, we need B equals F.
C equals 0.
We need C equals negative C. In other words, C equals 0.
Also B.
What's that?
E by the same.
E has to equal negative E, so E equals 0.
C equals
And I think we need one more thing.
D equals H.
D equals H.
Negative equals H. Yeah.
D equals negative H. Yep. I had a negative sign for one of these, I remember.
We have, but there's 2 other variables we haven't talked about. A
Oh
doesn't
dear.
matter.
They're
Oh dear.
A
What
and
about A and G? I guess they don't matter, do they?
Oh, that's so neat.
A and G can do anything
Maybe.
they want.
Maybe, Emily Rose, there's lots of different possibilities for what we could choose to be our alpha. I'm going to choose, for instance,
Aren't there,
how about A equals C equals E equals
EG might not
G
be the best
equals
choice of letters,
D equals H equals 0.
Q joins 0.
And B
What
equals
a fascinating.
F equals 1.
Okay.
So what does that give us? That gives us something that's actually not just in Q. You're right, if we set all of these equal to 0, then we just get, it's just Q. But that's, which is true. Phi of RS does fix everything in Q, because literally all of these automorphisms fix everything in Q. But we need to actually end up with something that's not in Q itself. So what does that actually give us for what our alpha can be equal to?
4th root of 2 plus I 4th root of 2.
Say 4th root of 2 psi 4th root of 2. And that is one possible value you could choose for alpha. Turns out there's infinitely many others you could choose. Because there's lots of solutions to what do A, B, C, D, E, F, G, and H have to equal that satisfy these 4 conditions.
Given that A and G can be literally anything.
Any rational number. Yes.
Let's do it for beta.
Now let's do it for beta. Well, if you do it for beta, you end up with something like 4th root of 2 minus I 4th root of 2.
Oh,
I mean, there's many other ways you could do it, but if you were to set up and solve the same system of equations, you end up with something very similar where it's like B has to be negative F, certain things have to be 0, certain other things have to be equal to each other, and that.
So in general, if Q adjoined for any alpha at least in this particular field extension, if Q, if we have a valid alpha, will its conjugate work as a valid beta besides 0?
Not necessarily.
You need the.
Because like if you took Q adjoined I and Q adjoined negative I, for instance, that gives you the same thing.
Well, yeah, I mean an alpha that actually will work for this,
Why wouldn't
right, such that
Q adjoined I not work? If we had gone through and finding what is Q adjoined I, if we had replaced that with some gamma, where that corresponds to the fixed field of subgroup generated by R.
Well, but alpha can't be.
Yeah, but
I just mean
I
for
is
this
not-
alpha.
You mean for this specific
yes.
alpha?
For
Yeah.
this particular alpha.
Yeah.
Yes, for this particular alpha,
If you find a valid alpha.
let's see. Yes, the fact that B and F have to be equal to each other, yes.
And does that just come down to the mappings are just,
That comes down to kind of the, looking at the relationships that get satisfied here.
and there's just a negative sign difference between our
Yeah.
and our keyboard?
It's crazy. This is the result of Galois theory. All of what we did today. Because all of what we did today will work for any Galois extension. In the homework 7, I basically just say,
Do it again.
do it again with x cubed minus 2. So basically, you end up with a degree 6 Galois, a degree 6 Galois group. Hint, try S3. I think I explicitly tell you use S3. You can also use D group, but I want you to use S3. Because I want to make sure everybody remembers what the symmetric group is.
No.
I'm glad I spent
I don't know,
hours
maybe because the
figuring
symmetric
that
group is going to
out.
play an important role in the next couple of weeks, and I want to make sure everybody has some practice with it so we can work with it.
That makes me feel a little bit better.
So where does that leave us? Technically, we need to prove fundamental theorem of Galois theory. We could do that. That'll probably take us another week or so. I'm a little bit more interested in going on to look at insolvability of the quintic personally.
Yes!
That's what
I'm
I was
guessing-
thinking about.
From your all's reactions that would be a little bit more interesting to you all as well. I wanted to introduce this theorem. A lot of the proof it's basically just spread out over chapter 7 in the textbook. There's like 20 different like intermediate results you need to prove. None of them are that bad, but it's just kind of a lot. I wanted to give you all one big example of here's what it all comes out to. Let you all do one on your homework. Maybe I'll put another one on the final.
Yay!
And turns out all of this is very much related to the insolvability of the quintic. Involves something called solvable groups.
Something tells me that you're going to be getting handwritten homework from me this time, Dr. Gerson.
That's okay. That's fine.
I always do.
Well, if you're too lazy to figure out how to do a lattice in tech, then fine.
I'm ready.
After the homework is completed, I want to see your lattice coding, but no, I don't think I'm going to spend.
I will say, like, there's a reason why in my packet I didn't have this lattice already drawn out.
I have an insane week.
Okay,
So-
at any rate, I think that'll do it for today. When we come back next time, we'll talk briefly about the formal correspondence theorem, kind of what does all this say in general, and then we'll move on to talking about solvable groups and insolvability of the quintic. Right. Hope you all have a good one. See you all Thursday. Parker.
Yes. I think I know what you want to do.
Bye, Lydia!
See you, Lydia.
Can we do